to be an assistant.
Oh. I got nothing. To say we were well prepared for this would be an exaggeration. In fact, it is an exaggeration. But I hope I'm primed someone to say something controversial. Steve.
Right, okay. I just walked in and Mike said, can you say something controversial because it's not done any work? So I'll say something that's not very controversial, and I'll say, I think we have more agreement, possibly, than we think we have. Maybe our only problem is that we talk two different languages. So it's this issue about getting a large-scale field, which again we talked about today. I think we would all agree that they're not very turbulent values, not very turbulent systems. The small-scale dynamo and the large-scale dynamo are very hard to distinguish because at small RM, the small-scale dynamo wants to generate field on a scale RM to the half, and that is not very different from a large-scale dynamo. You have a small RM, there's not very much separation scales. So therefore, there's no problem. The problem always arises at high RM. So everybody has the same problem. The question is then, what do you do? You either try and do something which may be a little bit simplified at high RM, and so then you'll always have the criticism that, oh, well, your flow is too simplified, but at least you get to high RM. Or you do a very complicated flow at reasonably low RM. And I think there's room for both approaches. I think that's the point. And the only way we're going to meet in the middle is to really push the simpler models to be more complicated and the lower RM models to be higher RM. I just wonder if anybody else had any views on that.
Thank you, Steve. Someone come back with something controversial. Igor. Nathan.
Yes.
Both at once, please.
It's really difficult to distinguish small-scale dynamo and large-scale dynamo with magnetic resonance number, several models. But because you from one hand generation of small-scale magnetic field, from another hand tangling of large-scale magnetic field which is produced by large-scale dynamo. But if we've got enough large magnetic resonance number, as say in solid situation and electric situation, of course it's possible to distinguish. Spectra is difficult, it's different. It's a problem of computers, not of science.
I mean, I would just like to ask,
Yeah.
how high or how low is low RM and how high is high RM?
I mean, this is the thing, it's fairly flow dependent. Okay, you take the Galloway property, for example, and you can say it's a funny flow, but it's a dynamo at very low rise. I mean, in fact, if you're allowed to go to whatever KZ you like, it's a dynamo RM is null.
Yeah.
And so, quite how high RM has to be is an interesting question. So it's very model dependent, and especially when you're at the low RM regime, there are some dynamos which are even, they're dynamos and then they're not dynamos, and then they switch on to being dynamos again. But once you get to high RM and your flow is sufficiently complicated, then you tend to get all your flow to being dynamos, and hopefully there should be some convergence, assuming that they do the honourable thing. But whether you can have something that's a reasonably low RM, which is a dynamo for some flows, you can add something to it, and then it's not a dynamo. It's very hard to then say that tells you anything about low RM, about high RM. So this is important information we're getting here.
You want me to bring this forward to 1710?
So we have enough.
Axel, do you want to comment on?
Enough discussion.
And the drinks?
All's just been said. They're not on the drinks.
Yes, I have a comment.
Oh, sorry.
Yes. There is this ability to separate the large-scale dynamo and small-scale dynamo. Even your Reynolds number, magnetic Reynolds number is high enough. If you calculate the energy transfer rate between different scales, you can find out if you have non-local transfer rates from small scale to the large scale directly. then it is a large-scale dynamo, in some sense.
Well, it could be a large-scale dynamo, but is it a large-scale dynamo as envisaged by mean field theory? That's not necessarily the same thing. I mean, I can see that there might be some way that it has a turbulent flow. It produces a magnetic field with a given spectrum, but it seems that that spectrum is peaked towards low k for some reason. It may still be that, according to mean field theory, you don't get a mean field as described by mean field theory. But I think we'd all be happy with something that gave us a significant amount of power at small k via transfer. But it may still, if you calculated alpha, have a, you know.
But what about inhomogeneous MHD turbulence?
Right.
So you can imagine a model problem in which you have MHD turbulence, which is basically small scale, but the thing is modulated over a much larger scale. Now, how does that differ from a large scale dynamo? You're bound to get a large scale field out of that.
Well, can it sustain?
Well, I'm just asking how we distinguish.
Well, you have to integrate for long enough.
Well, what would be the signature? Already, you know, the turbulence itself has a long length scale because of the long scale modulation.
Oh.
So there's already a large scale magnetic field. How do we know what's the difference between that and the mean field dynamo?
My personal feeling is that they're all small scale dynamos because, you know, in some sense, like if you look at the sun, there is a large scale flow. And somehow the question is then, how can you get it to be a small scale dynamo but with a significant amount of energy in the larger scales or in a large scale? That's just my opinion.
Why did you say in inhomogeneous dynamo, inhomogeneous MHD turbulence has large-scale fields?
We must have large scale components because it varies on the large scale. So there must be something that varies on the large scale.
Yeah, but it could be the turbulent intensity. I mean, a large-scale dynamo is something which actually has a large-scale field, which means as an average that you can define, which is
You're
finite.
not suggesting it could be a rapidly varying large scale field, and therefore it wouldn't be a mean field dynamo.
It could be a rapidly varying field which varies, and the turbulent or the magnetic the B squared intensity, of course, varies over a large length scale. But this does not mean that the average still is finite. It can be exactly zero at every given point, but B squared is finite.
I think if you look in Fourier space, naively at least, you won't have additional power and noise scales just by doing that.
No, it's true. Well, if you just suppose you have some MHD turbulence in a sphere, right?
Okay.
Now, I don't know what's going on inside, and I examine the dipole moment.
Right.
Do you expect the dipole moment to fluctuate wildly on the shortest scale?
No, it's going to do a random walk.
If you will wait enough long time and produce good average, as we've done in our laboratory, you will, if you've got large-scale structure, you will reproduce it. If not, not.
For the situation you just described, you'll have a dipole field which will satisfy the fluctuation dissipation theorem. So it'll be persistent for many cycle times, but it won't wander.
Right. Yeah, so but it's not far away from something. You may not need it very much more to stabilise that.
Well, it's probably good sequence.
So, I mean, reinforces Steve's point, really. It's quite hard to distinguish what's going on. Yes?
And by the way, if you just have an inhomogeneous system as opposed to a homogeneous system, if you think of the simplest generalization, that was already studied by Pat Diamond and Gruzinov. So if you take turbulence in a situation where you have a vertical field boundary condition, then you do generate an inhomogeneous system by introducing boundaries on the two ends, and the result is that that you do get a large scale field, but its amplitude decreases. B average squared decreases like 1 over Rn. So in this situation, and that's not well appreciated perhaps, you do have a catastrophic saturation value. And that is explained by magnetic helicity conservation, or losses rather, of both large scale and small scale magnetic fields at the same time.
I was never wholly convinced by that.
So that is, sorry, what?
I wasn't wholly convinced by the analysis in that paper.
No, but we reproduced the same result through numerical simulations. First Wolfgang Doppler and myself, and then more recently in a paper with Kanaswamy in 2005.
Okay.
So those results are actually correct.
David?
I mean, the only true way to determine a large scale dynamo is that it doesn't exist at small scale. You can imagine a box. And
Can you speak a little louder?
you calculate alpha and you calculate beta in your box of turbulence, and there isn't a dynamo. And you make a box big enough, and it's a dynamo. That is a genuine large scale dynamo. Because if you shrink a box, it goes away. Whereas, but if you've got a turbulent flow and you make Rm large enough, you never really expect to be in that situation because you always expect a dynamo on the scale of the box. And so it's very hard to have a large scale dynamo without a small scale dynamo, and that's the problem. And so, and then if you calculate alpha and beta in the presence of a small scale dynamo, saturated, say, then you can say, okay, I've calculated alpha and beta, what do they tell me? And if you're, the most optimistic thing you can say is, they'll tell me about the growth of something large given those alphas and betas. And if I had a box even bigger, I get the growth of something determined to be growth rate alpha k minus beta k squared. And then you say, if I did that, is that really what I would see? My feeling is, well, there's various competing things, because you've already got the small scale thing sitting there. You say, right, I'll make my box 1,000,000 times bigger so that this alpha feature can come up. Well, no, because what will happen is that this small scale dynamo will kind of go eek. It's got a bit more elbow room, and it will stretch out to the ends. And that's what you're seeing. That's what you could see. So there's no guarantee that having calculated this alpha and this beta, even if you can calculate it, that you will ever see something like that. I mean, Nathan will say, oh, well, if you average forever, like in his lab experiments, you'll see it. So what does that mean? It means that you've got lots of dynamos in lots of different stars. None of them have a large-scale field, and then you take an ensemble average of all these things, and mysteriously this large-scale field emerges. But that's never what you see. If you never see it, it's no use to you.
But in principle, you could have, leaving aside inhomogeneity, a homogeneous situation of MHD turbulence, stationary averages and so on. You could look for an instability based on long length scale, long time scale modulation. And I suppose if that existed, you could call that a mean field dynamo. Or would people disagree? But no one works in that way, actually. I mean, that would take place on a much longer time scale than the establishment of the MHD turbulence, of course.
Yeah, then it depends how the MHD turbulence reacts once that thing
gets going.
Yeah.
Yeah.
And it can just kind of stretch out a bit, squish you otherwise.
Yeah, well, yes.
So what about on the same lines but even simpler? Just consider one harmonic, one wave, and modulation. So modulational instability does it exist? That's easy to check.
Yeah, I mean, I think that's, one could imagine a toy problem in which you did this with some existence. The trouble is, you have to do the turbulence properly, and you have to get the interactions right, even if it's only a linearized departure from the uniform system. It's tremendously difficult to compute. You have to find the adjoint of your turbulent system. How do you do that? Find the I don't know.
It's possible to do the linear problem by looking for subharmonic modes in space, but
Yes.
then getting everything to saturate at the right levels. I mean, you can look at growth rates of subharmonic modes for simple flow. You can do it for the Galloway-Proctor flow.
You could. Absolutely.
Yeah.
But
and you can look at the growth rates, but it doesn't really address David's question.
no, it doesn't, because something might happen later.
Yeah.
That's true. Come on, a bit more fire, a bit more controversy. We'll look half asleep. Come on, Nathan, stir us up.
On threshold of large-scale dynamo, we've got possibility to organize some averaging in some intermediate time scale, and from one hand to keep exponential growth, from another hand to filter all small-scale stuff.
Well, that's what one would like to do, and that's sort of like mean field dynamo theory in this non-linear regime. But how to do it properly, I think.
It's not non-linear. It is intermediate, how to say, time evolution will be, in the beginning at least, linear.
It would be linear. I think what David's point is that it would quickly become non-linear, and something different would happen. Well, we have to wait many millennia.
Not many.
It's not a trouble for us.
Many to know what time. If you enough lucky, you've got enough strong computer or enough strong brain instead of computer, you can do it. It's difficult, but it's possible.
My parallel processing powers, Nathan, are very poor at this time. Go on, Axel.
I think we really want magnetic fields that are already clearly visible as having a large-scale component without going through the exercise of terrible averaging. So many of the dynamos that we have looked at do actually have this property, including the astrophysical dynamos like the Sun and the galaxies. So the really good ones don't really are not really hidden large-scale dynamos. They're very evident. Large-scale dynamos, as was brought up already a few days ago, do have a threshold, and the threshold is different from the threshold of small-scale dynamos. So it's very important to identify this threshold. The threshold does depend on the scale separation, but it also, of course, does depend on the degree of helicity that we have. If the degree of helicity is, for some reason, strongly perturbed and very small, in Petrie's experiment, for example, it was probably very large because the fluid Reynolds number was fairly small, and therefore it was fairly strongly organized. Clearly, if we go to larger fluid Reynolds numbers, the relative helicity will decrease. That certainly must have an influence. And so we need to calculate, of course, what is in any given case the critical dynamo number. The critical dynamo number we know from the mean field theory. It's not the microscopic diffusivity doesn't enter here.
Right, but if your helicity very big, you should need to organize calculation in huge box, because you want simple very large, nothing else.
Yeah, and we need to know
how big. Very strong scale separations, again, new problem for computers and for brains.
Yeah, the Sun, of course, has an entire phi direction and has many other, and so it has a big enough scale relative to the scale of the eddies.
One would hope. I mean, it must have. In some, of course, we see how large scale field. Yeah.
I wanted to say something different, at least in the context of both galaxies and clusters.
Oh, very good.
Plasma. The microscopic Reynolds number calculated with the microscopic or a Spitzer resistivity or a Spitzer viscosity type things. I mean, the magnetic Reynolds number is huge. And it looks completely unrealistic to expect the system to have a magnetic Reynolds number of 10 to the 20 or 10 to the 19 or 25, whatever. And there must be lots of other processes which come in and change the collisionality of the system. Definitely in clusters, possibly to do with plasma waves and things that you have not taken into account. And so I suspect that the magnetic Reynolds number itself will come down. So when one has to keep this in mind when thinking about large magnetic Reynolds number system. It is possible also that the effective magnetic Reynolds number in some of these systems, like a galaxy, may not be 10 to the 19, but maybe whatever 10, several hundred or 1,000.
Yeah, absolutely.
And that would be good for you.
Yes.
if it does. But of course, the calculation of such a quantity is not yet there. And how exactly this will happen, whether through some waves being generated and wave particle scattering, resonance scattering or something. This is something which is also worth keeping in mind when thinking about Reynolds numbers.
But the Braginski viscosity, for example, that you may have perhaps had in mind, I'm not sure that this produces any cutoff in the turbulent cascade. Is there any evidence that it does produce a cutoff?
But there is no MHD beyond that cutoff.
Yeah, but no. All I'm asking for is to calculate a power spectrum, right? So then you calculate the power spectrum at small scales. Even if somebody says there's no MHD, you can still measure velocities. Can you not?
No, I agree, Axel. All these things are cut off only at some gyro scale or something eventually, all these spectra. But question is, when you're calculating resistivity, at least in dilute plasma, I don't know about the Sun, then you are using the mean free path from Coulomb collisions. But there are all these plasma waves, maybe at the gyro radius, which you can generate before Alex Shekoshin.
Yeah. Actually, I think what I really meant is, regardless of the reality, we just take the Braginski viscosity as if it was the real thing. All I want to know is if the Braginski viscosity should have a dissipation wave number within your simulation box. My question is then, does this introduce a cutoff, a dissipation range in the turbulence or not? And it may not. So it may still blow. It may still only produce a cutoff at a much smaller molecular viscosity that you would still have in the numerical model.
Awesome. Cutoff, you mean the energy converted into heat?
Yeah, right.
That's always going to be.
Or at least
this always happen at micro scales.
No, it could happen through waves, of course.
At very small.
If you generate waves, and the waves are damped,
Some non-linear viscosity, maybe some non-linear viscosity, it's similar to non-linear conduction.
So no cutoff then. Do you all agree no cutoff then? Or what?
I think you need a real molecular process for cutoff.
You're the chairperson. You speak loudly.
Stand up.
Let me ask some questions. Maybe
Let's have a statement.
why don't you say what you wanted to say?
All right. Can I?
Yeah,
You're in charge.
general opinion that, for instance, interesting question, believe me.
Never mind.
General opinion that source of turbulence, at least in stars, is convection. So if no convection, no turbulence. But pay attention. For example, we will take a non-convective star, just radiative processes. But nevertheless, we have got in this system, say, Eddington circulation. Am I right?
Eddington, yeah.
So if we now calculate Reynolds number of this circulation, it will be huge. My feeling that if we've got some shear, never mind what the result is shear, maybe differential rotation, maybe Eddington calculation, we definitely will produce turbulence. Of course, this turbulence will be much more weaker than the convective one, but the effective parameters will be huge again compared with molecular. So my feeling that we never have in astrophysics non-turbulent situation.
Mm-hmm.
What is your opinion?
Yes.
Definitely answer. Excellent. Sridhar, what you wanted to say, Sridhar?
Oh, about viscosity. If I recall right, there are at least three viscosities, three Braginski viscosities. Okay? This is for the collisional nature. Okay. Please correct me if I'm wrong. I'm trying to recall from what I read many years ago. So the kinematic viscosity generally has units of some length squared by mean free path, so some length squared by time. The usual one is mean free path. What's the mean free path? It's just Coulomb mean free path divided by collision time. Right?
I think you want to square something.
Oh, yeah. Right? So this is U1. Then there's another extreme where the Braginski case, this is the Lama radius squared times gyro frequency, or Lama frequency. Correct? And there's something intermediate. This is clearly dissipated. This is non-dissipated actually, because it doesn't refer to anything collision. Okay? Correct? Yeah, it's a viscosity, but it doesn't convert, I think, kinetic energy into heat.
But not really.
Okay, it does something else. So this is the collisional regime where you have three different viscosities. And I think somehow the Alfvén wave is not much affected by any of these. Okay, it's divergence, it's incompressible, and it's somehow not affected by any of this. Now, this is only for a collisional plasma. For a collisionless plasma, none of this is relevant, Rob. Okay?
Yeah, I mean, also you should remember that the resistivity and the viscosity go differently. So,
Well,
if you increase the amount of collisionality of the, in some sense, then you will increase the resistivity, but you will decrease the viscosity.
That's in the usual Spitzer description.
Spitzer description.
But for a collision-less plasma, what is damped, I mean, what happens is something like the magnetic analog of Landau damping. Okay, that you have these waves which create some magnetic bottles, and particles, electrons bounce back and forth, and then there's wave-particle interaction, and this robs the energy from the waves. Okay, so this is completely unconnected to these. Okay, and this is this would give rise to sort of a damping at the gyroscale. Okay, at the gyro radius.
No, I think it's larger. For compressible modes, this in collision-less plasma, this damping scale is much larger than the.
For the compressible modes, for not for the alpha mode.
For alpha modes, yeah, alpha modes is.
Okay, maybe that's what I recall. Okay. For alpha modes, it's I think cut off at the gyro radius. Maybe you're right for the compressible mode.
But why ambipole diffusion isn't mentioned now? It converts magnetic energy into heat.
It doesn't, I think.
Why not?
No, it converts magnetic energy into heat, but
Ions
preserves the
collide
flux.
with
But it-
neutrons.
But preserves the flux.
Yeah. But I mean, it certainly doesn't introduce a cutoff in the spectrum, as we found in 2000.
It just
But,
stops,
let me try to understand.
it just stops being one fluid, so it just reaches gyro radius, and you convert to other ways, which is normal, right? Which have wave numbers bigger than inverse Larmor radius. There's plenty of non-dissipative waves below that. So you just have non-dissipative crossover to that. So it's not really good to say what happens to alpha wave, because it stops being alpha wave at that scale, right?
So it's
But you can think, when you can sort of define your internal degrees of freedom as anything that happens below the gyro radius, and then from this point of view, it is heat, it is internal.
That is true, but it could MHD limit could well break down before the gyro radius, and you might have to take into account what Hall drift waves. Is it that?
Hall, yeah.
Hall waves of which there is
Yeah, that's it.
I think
Depends
who's
which
this?
set.
Elliot Quaitert and Gruzinov did this, right? Anyone remember?
They wrote about this.
No, something like that.
Yeah.
Okay.
You will have drift alpha waves instead of pure alpha waves because of the different inertia of the ions and electrons. And we have shown that if you take into account this two-phase effect, that means different motion of the ions and electrons, if the suppression in the turbulent transport that we found in the single fluid is little less, is little weakened. So two-fluid effect somehow help you in the reduction in the transport. We didn't look at all possible two-fluid effects or the cumulative effects. We just looked at the ion inertia effect.
Polarization drift. That's what you referred to, right? So inertia of ions. So you kind of like you don't go too short, but you go to sort of frequencies become bigger, right? That's what she's talking about. So if you take into account ion inertia, so that you are then you have correction to E cross B velocity.
Ah, okay. And sorry, I missed something.
No, the bottom line is if you include the different motion of ions and electrons, I mean, in MHD model that you have with music, the ions are tied into the electron motion. So if you separate the different, I mean, if you differentiate the motions, I mean, if you go on to the small scale, the ions really are not tied into the electrons, they move differently.
I mean, my impression is that the usual MHD resistivity can be modeled in this way by treating two fluids which are sort of tightly coupled, and then there's some sort of a relaxation effect where the Lorentz force is balanced by collisions.
You probably
So
thinking of three
the two
fluids.
fluid thing is in the resistivity. It's already there in the MHT limit, right? Wouldn't that be true?
No, but not waves. She's thinking of waves.
No, waves, is it? Oh, I missed something. Sorry.
The single fluid model, I mean the single MHD fluid model assumes the ions move with the electrons.
To a degree, but there's a drift velocity, there's a relative velocity which is responsible for dissipation.
Yes, that is true.
Mhm.
But I mean, there is other effect that makes both of them the motion of these two species different. So for instance, if you go on small scale, I mean, if you put a strong magnetic field and ion gyrate with some ion radius,
Yeah.
while the electrons cycle with a smaller ion gyrate radius. So if you go down to the scale which is smaller than ion gyro radius,
Okay,
you have different motion of ion and electrons.
sure.
So now if you take into account such a two fluid effect,
Yeah.
which you cannot really describe by single fluid MHD equation, you need to solve the equation for the ion and
Okay.
the electrons.
Okay, okay. I understand. Okay.
And then if you do that, I mean, that the different motion between the ions and electrons will help you in the turbulence principle.
Okay, I think I understand what you're saying, but it seems to be on scales which are smaller than the ion gyro radius. Whereas we think other effects would likely dissipate things on larger scales, even before you get to the scale of the ion gyro radius.
No, that depends
No?
on the collisionality. You can have the ion, the only distributive scale, which is even smaller than ion gyro radius. It depends on the temperature of the plasma and ion collision.
Collisionality, okay.
That's precisely what you said yourself earlier, that viscosity on the bottom is not going to stop cascade. So that just means
That's in a collisional plasma.
without collisions,
That's right.
you're going to take all your energy below.
That is true for a collisional plasma. See, this is in the Bragginski limit. Okay, when you're not in the Bragginski limit, okay, this sort of description is invalid. I mean, you have to do kinetic theory.
Yeah, I had just had a comment on this electron and ion differential motion. So the relevant parameter, I think, is the so-called ion inertial length, which is the speed of light divided by the ion plasma frequency. So that depends only on the electron, only on the plasma density, basically, C or omega pi. So that's the below that scale you have to have a two-foot model. So I mean, you have to include the so-called Hall term, which is in the Faraday's law, which is proportional to the velocity difference between electrons and ions.
But is the Hall term dissipated?
No, but it modifies the solution. So the Hall term generates kind of Whistler waves,
Yes.
and also small scale. It tends to generate kind of small scale flows.
So the question is, does any of this change the effective Reynolds number, magnetic Reynolds number? Probably not.
It could by a few orders of magnitude, but does any of that change dynamo theory? I mean, if it changes from 10 to 22 to 10 to 15, would it settle differences here?
No.
No. All right.
Can I come back for a second?
I can make one comment to that. If we have a dynamo which is in steady state, statistically speaking, then it's marginal. It's not highly supercritical. The flow which gives rise to it must be a marginal flow, otherwise it would grow further.
So how much large-scale energy is enough for you to be satisfied? You know, let's say it's large-scale dynamo or some other mechanism. I mean, like in turbulence, with neutral fluids, you know, there are distributions based on Safman invariant or Latiansky invariant. You know, there is some sort of growing power distributions. So would that be enough, or some equipartition of energy, perhaps? You know. So I mean, what do you try to achieve? Some big spike that keeps growing, or would that be just some power law distributions at large scales, and would be good for.
So I'd be quite happy with a statistically steady field that exhibited large-scale characteristics. In other words, had a significant amount of energy at the large scale, so you could see it. This seems to be hard to find when the.
No, it's easy to find, it's hard to calculate.
Well, but where? We've said it's easy to find.
But it's easy to find in the universe.
I didn't mean that, of course. Excuse me. Yes, you're absolutely right. I use my words back. It's hard to find with our brains and computers.
With our eyes, it's easy.
Yeah, the eyes are easy. Yeah, yeah.
Level of magnetic energy depends on the level of flux of magnetic helicity.
I was quite intrigued by the simulations that Rodion Stepanov showed, which produced a peak of the magnetic energy at a scale which was by a certain factor smaller than the position of the kinetic energy peak. Secondly, the magnetic energy was in slight super-equipartition at that scale, at that wave number. And then at larger wave numbers, they became very much in equipartition again.
Smaller wave numbers.
Larger wave numbers.
This plot, it's usually about, it's in all scales where magnetic field is saturated, it is about from 1.6 to 2, the ratio. So it is in steady state, more or less, statistically steady state, it is it's a factor of 2 larger.
Yeah, and that's exactly what the simulations showed.
Yes, I know. I have seen.
But that's but this factor of it's different at the position where the magnetic energy peaks. The magnetic energy is in stronger super-equipartition than at larger wave numbers. I mean, of course, before the dissipative cutoff, clearly, but it's further into the inertial range.
PM less than 1 or greater than 1? There are 2 of them, right? So you have two set things.
Make a sketch.
You have 2. One PM very much less than 1, the other PM very much greater than 1.
So,
Let it go.
You can sketch.
I can because I think my presentation on the laptop.
If you.
Just use this.
we know what the bricks are.
So don't touch the dinner, actually. Don't touch
In your plot, the kinetic energy looked like this, but then the magnetic energy showed something like this. And then it became closer to it, and then of course it drove off further. So here I'm saying there's super-equipartition, or in this regime here, super-equipartition.
This was small PM.
Yes, it's more or less.
It didn't even matter whether it was large or
No,
small.
in large PM it was different.
No, it just affected differently. But what I would and that is, I find it interesting because that's exactly what the simulations, of course, show. But then you made some statements about fluctuating alpha, which then you didn't have time to talk about. What was that all about?
Yes, that was the paper we published. We use the simplest model for large scale dynamo, alpha square or alpha omega dynamo, and we use the shell models to calculate some transport coefficient like diffusion and alpha. And we find out even the mean value of alpha is 0, there is a large scale dynamo. At some, there is, of course, there is some threshold of for different. Look, can you? Maybe this plot is interesting to see again in more details. So dynamically, so the one moment is dashed line, black one dash. It's kinematic energy, and kinetic energy, and magnetic energy is the red one. So before the saturation, it was like this, and after which is solid line, you see something like this. But it is dynamically. At steady scale, it is different, and it looks like. So here we didn't see clearly, but what we. So this is a plot I had all time. So it's a ratio of magnetic energy to the kinetic energy at each scale, and what we see for large Prandtl, it's the dash line for the small Prandtl number. This is for the large Prandtl number, and we see it is almost the constant, and something different here. But anyway, in inertial range, it is about 0.6 or 0.8 maybe. So it's a quite stable value here.
So what is plotted?
It's a ratio, sorry, it's a ratio b
Oh, I see.
divided
Oh, I see.
by u square.
So you're saying it's constant?
Yes, it is.
But then look again at the plot.
And it's larger than 1. Wait a minute, but it's constant, but it's larger than 1.
Yeah, 2.
1, yes.
2. So super
1.5.
There, I see the problem that it's not clear that it is larger than 1. Okay. If you want, yes.
Oh, I see. Maybe it becomes.
This plot.
I mean, here, for example, you clearly see that it jumps over, right? The red line.
Yes, but finally,
Yeah.
kinetic
But show again
energy-
the animation. If you show it.
Yes, yes.
And for large PM, it's even stronger on the right plot.
Mm.
So I try to.
Mm-hmm. Maybe it's useful to plot compensated spectra in the future. So here,
Yeah, actually it's different.
Yes, in the future I can quote it just to. But, so do you mean this?
oh, I see. Yeah, that's different. Yes. Yes. Okay, that's large Prandtl number, and then small Prandtl number again. Yeah, here's absent the thing.
So, so many.
Yes.
So just this moment is.
Yes.
Okay, it's clear, and then.
Yes. Isn't that clear? It clearly goes above.
Yes, yes, it's gold, but it is not here. It is a bit later.
Yes. I see. Good.
Why don't you ever force from some intermediate scale?
We have such result.
Yes,
Yes. You can have a look. It's really nice to see the spectrums for in infrared and.
Right.
May I ask you a question from the observer's point of view? So we're always trying to find something we can understand and something we can maybe also use for observation. So what is observable? And from Rodion's talk, I tried to learn something and just would like to ask you or the audience here whether this is a correct view. So to my understanding, this gives us an interesting tool which could be tested by observation. So as you know, in galaxies we can look back into time, and hopefully with the SKA we will be able to do that. So would it be a reasonable point of view to say this model gives us a tool to understand how magnetism develops in early galaxies until times? Because you're already giving growth times for different scales. So is this something we could use to argue galaxies start with relatively chaotic and then slowly large scales build up, and so even times could be given, growth times could be given, and maybe even in real units we could use as observers. So is this a reasonable view, or are there objections against this simplified view about evolution of magnetism in galaxies? Somebody comment on that?
No, I can comment. You never get something for nothing in this game. I mean, you just don't. Dynamo theory, if it looks too good to be true, couple of years. Now, the question is, as Axel put it in the talk, these models that have been around since the 70s, and they do remarkably well in some circumstances. In other circumstances where the phase information of your flow is important, which is in almost all astrophysical or geophysical flows, because you have certain things occurring in certain parts of space, so they have non-trivial phase information, like you have water systems or you have something like this. And this throws away the information that you need. So you can have two flows which have the same spectrum and therefore have the same description by this thing, one of which might be great dynamo, and the other one might not. So you have to treat it with caution, and it agrees well with homogeneous isotropic simulations, and I think that's amazing. But you might want to be careful before using it in non-homogeneous, non-isotropic, rotated, stratified, anything like that. You should proceed with caution. But one question I would like to ask is, it does really well in the homogeneous isotropic.
Yes, I agree. We can expect at small scale that the statistics is enough to consider as homogeneous in some sense. But at large scale, we have only a few turbulent cell, or we have only one galaxy in the size in the observational frame, so we have no statistics for. It's not chaotic.
But there is a billion of turbulent cells inside a galaxy, so there is more than enough statistics.
The observers always increasing in the largest scale, small structure.
But a given galaxy contains about billion of turbulent cells. If there is not enough statistics, I don't understand what does it mean, statistical approach. In my opinion, we have to give a positive answer on the question formulated by Rainer. If, of course, maybe our understanding of galactic dynamos at all are primitive, preliminary, and so on. But if we will not try to apply them to such option which can be provided us by observational astronomy, what can we expect?
I mean, to answer Rainer's question, I think what this model of Rodions shows and what equivalent direct three-dimensional simulations show is that there should be basic equipartition or a departure of equipartition by a factor of 2 approximately. And that is, in some sense, a fairly robust prediction. It's slightly surprising before it actually emerged first from simulations. But now it's confirmed by several simulations, including even these shell models. So that is the prediction. And the question then, of course, that I asked Thorsten already, of course, but it can be shown, is whether the kinetic energy, the spectral kinetic energy, is in super or sub-equipartition. And then he said we cannot measure this. And so why is that? Why can I not measure velocity fields at the same length scale where you can measure the magnetics? Is that really true also in the future, or can we do something in the future perhaps?
We would be able to measure it. We would have already measured it. Astro E2 wouldn't have died.
If what?
Astro E2.
Astro E2?
Satellite X-ray
should measure
okay.
X-ray lines with high accuracy, and that would have been the perfect experiment in order to measure the velocity growth in England in these clusters. So there's no principal problem to measure the velocities.
So then that's for
high resolution.
You mean clusters? See, in the sound medium, Doppler shifts are readily observable. Still, this information isn't available. In the ISM, there are lots of Doppler measurements, no thermal line broadening. Still, nobody knows of the spectrum of turbulence and how it compares with magnetic energy.
So in this sense, don't think that this satellite object is low.
Okay, measuring the spectrum is.
But even RMS value, people still don't know what is the 7 kilometers per second for the RMS velocity is the best I know. But is it 5 or is it 8? Can you tell? No. Even the RMS value of turbulent velocity in the 7 medium isn't known.
No, but you know in the cluster, I think.
To that accuracy. Because this is the accuracy Axel needs, 10%.
I think it's not as bad as that at least.
And you need it as on different scales, right?
We need it as a function of wave number. We want to do a Fourier transform, yeah.
Yeah, this I honestly don't understand. I agree with Axel. It's totally unacceptable. With this history of radar astronomy, decades, not knowing what is the Fourier spectrum of motions which are readily observable through Doppler shifts. I also don't understand this.
This to you.
So that's your answer. So it's
So you're
all is
measuring velocities in galaxy clusters is hard, but nobody has measured so far.
In galaxies it's simpler, but you need different resolutions. So at large scales it's possible, and there are much better data than 10%. I would say this is rather safe, but to really have a spectrum to go, then you need high resolution, then you lose the flux.
Go to Milky Way. There is a Milky Way around.
Can we move from the Milky Way to Steve Tobias?
Can I just ask it on this, because we're talking about we need a spectrum, we need a spectrum. Is this coming from the theorists or from the observers? Can the observers give us a spectrum, therefore we as theorists calculate a spectrum? Or is it coming from the obsession and turbulence theory with spectrum? We come to you and say, we need a spectrum. Because my feeling is these things are inhomogeneous, and you see things in real space. So we had a talk this morning about trying to work out where the bends were by calculating things where if you just look in real space, there they are. Right? So you go through some elaborate thing to see spectrum of the magnetic tension in whatever, in spectral space. So is it coming from turbulent, from the theorists, or coming from the observers, this kind of obsession with spectra?
I think observers, they don't like that because there are lots of things which can produce scales, spatial scales, a lot of proper motions. So there's a lot of things going on in any sort of objects. So to really to be sure what you see is a turbulent spectrum, we are never sure about that. So there can also always be something hidden, like expansion, systematic motions which are hidden somewhere in the spectra. So that's why observers are normally very cautious in talking about that. And for us, a spectrum is a frequency spectrum, not a wave number spectrum. So that's why it's coming from the theoreticians, but observers, they have a hard time to provide really good data.
So it's awful.
But
Please, Anwar.
there is another effect that astronomers systematically prefer to observe unusual regions, which are bright, have a strange shade, but instead you need to observe boring grey regions where have quasi-homogeneous turbulence. And nobody observes grey, boring regions. Everybody observes bright and
yeah, right, exactly.
You just said something has a strange shape.
It's similar to media.
And that's very hard to describe in spectral space. If you're going to tell us tomorrow that there's a better way of doing it in real space, right? And therefore, I don't think we should have this obsession with spectrum.
Yeah,
oh, yeah, this is true.
But pointing in the right direction. So if you can't extract from observation, since it's so hard to extract from observation directly, the quantities the theoreticians are using, like spectra and so on, if it goes the other way around, you have to take the theoretical pictures and translate them into data space and compare them with the features which are prominent and ignore the features which you can't see.
Okay, so the theoreticians are doing homogeneous isotropic turbulence because in some sense it's easy.
Yes.
It's a theoretician.
So
now, and then they can because that's the natural thing to do.
So
and so you should say no, we're not looking at something that's homogeneous.
Yes. We have stratified atmosphere, we have clusters, we have gravitational potentials, we have all this at the same time, and it's a mess.
Yeah.
But some of the features of the turbulence theory, which might be valid in the homogeneous space, might still be valid in this mess. And if some of these things survive the observational filtering, then we can be able to discriminate between those.
But
and if not, then not.
Yeah, but whether spectra are the best way of doing it, I'm sure it's not. So I think the theory
let Peter have it.
Just to pay attention for this kind of model, because what Rainer asked, how we can compare the model and what will be observed. So Rainer expect to have in few years some 100 new galaxies, young galaxies. This kind of model, I mean the combination of shell model and a large scale model, reproduce also some realization of that. And the model is fast enough so we can easily reproduce some hundreds of this kind of realization and make statistically comparison what Rainer will obtain. And so this is because it's impossible to do things like this in a DNS. In the shell model it's no large scale dynamo, nothing to compare, and this can be really a good compromise which give us some possibility to make this kind of
I'm very confident that you have included all the relevant physics there.
May I make a short comment? Our discussion looks similar to a behavior of financial tycoon who is sitting with all pocket full of money and say how poor I am. Thinking about stellar dynamo, solar dynamo, geodynamo have qualitatively less observational information. And people, for example, people dealing with origin of solar magnetic field or evolution of solar magnetic field have to discuss something, what happens in the base of convective zone, from where comes completely no direct information. All what they have are very remote tracers of this activity. Galaxies and galaxy clusters are the only example when we can see directly in the domain where dynamo is presumed to be active. If we will refer this situation as very difficult, in which nothing can be said, friends, people who distribute money will hear it very soon, and invisible future, no one project will be supported. Please think, what are you speaking about?
Thank you, Dimitri.
I have a question for...
very optimistic prediction.
A question for the observer. Something about speculation. See, you can have come to some tentative conclusion that you've seen something to do with turbulence. If you can resolve many decades of some spectrum, right? For instance, and it looks like a power law, then it gives you some confidence that you've taken some mean effects out and you're left with something random and you're seeing a power spectrum. Now, as far as I know, in the best evidence for some sort of random fluctuations in the interstellar medium comes from the spectrum of electron density fluctuations. It's thought to, give some information on turbulence, but the direct evidence is for electron density fluctuations, and one probably has a power spectrum extending over 9 decades or something like that. Okay? Now, this is unmatched in almost any field. Okay? To have a spectrum over 9 decades. Now, this comes from mostly diffractive scintillation on small scales and refractive scintillation on large scales. Now, my question to observers is whether you can think of something where there's an analog with regard to Faraday rotation. So let me rephrase it. This diffractive scintillation comes from comparing phases along neighboring paths over very many scales. Okay, and it's actually interfering these two, looking at phase differences, not by doing something incoherent. It's almost looking at one wavefront. Okay? Otherwise, you will not have this fantastic detail. So is there an analog that you can think of where you can do some Faraday rotation correlation?
In time.
No? It should be coherent detection.
From Faraday rotation, it's not a scalar, so it's something which depends on the field direction. So that makes the things extremely complicated. It's shown in cluster. So in principle, that should be possible, but in practice, I'm very skeptical whether you can disentangle. The field fluctuations and the electron fluctuations are physically just different. So they are something which are probably also not related. We don't know. So that makes the things hard.
No, that's all right in the sense that's in interpreting data. Right? You're talking about the magnetic field fluctuation and the electron density fluctuation.
Principle, something like
No,
that.
I'm talking about at the detection end. You see some swing in polarization. So let's forget about trying to disentangle B parallel fluctuations from any fluctuations. But just in the process of measuring, can you do something that's similar to detecting diffractive scintillation?
Well, you can do it through a galaxy cluster. The same physics which works with a galaxy can work there. It just needs a proper source and sensitivity, and probably have to go to them pretty low frequencies because the electron density is lower by a factor of some.
Okay.
And then you might learn something about density fluctuations. But the difference is, in the galaxy, we are sitting right in the middle.
No, it doesn't matter in the sense that we are still sitting in the middle of, let's say 2/3 of the way out. Okay? And it's not a matter of interpretation. What the effect is due to. Finally, we measure something. Okay?
No, the scales are bigger, so you may have longer time scales for normal scintillation kind of thing.
Yeah.
But remember that in that meeting in Manchester, which I think Brian was there was, who was that, Rickett, who was talking about broadening of distant sources because of intergalactic turbulence, right?
Yeah.
In the Lyman alpha forest thing. So it's possible to not do time thing, but it maybe if you want to have a angular broadening of very small images, that is a different thing. But rotation measure, things have to change, right?
Simulations are so fruitful because it's time variation which is observable.
Well,
and here you have integral on line of sight.
Something has to change. Either you have to move very fast.
No. And time variation is mostly because some diffractive screen is moving across.
Correct.
So the same thing would happen with rotation measures.
But you have
some
to move,
frozen stuff.
But suppose the correlation scale is 100 parsecs and you have to move.
You
have to move. You move in a few hundred years or something. You only move at speed. So.
That's for the galaxy, you mean?
Sorry,
no, but not if you have a power spectrum of fluctuation, right? You're talking about the large scale.
Yeah.
We have to increase the frequency of contributions because the time remaining is only 1 minute.
All right.
Does anybody else want to ask? Nathan, please.
2 minutes.
No, 1 minute.
1 minute.
Because we need the
It's
drink.
definitely not enough.
Well, speak very fast.
Yes, I agree that people in galaxy much more lucky than the solar guys. It's true. And maybe people which normally work many years in dynamo, in solar dynamo, should, how to say, step by step to diffuse to galaxy. Maybe it's much more healthy.
That is a manifesto for the future, thank you. Well, I think we must draw this to a close because somebody's got to pull the corks out and that's what it's going to be excellent, is that right?
No.
No? But anyway, thank you all for contributing.